Again, thank you everyone for coming. And first of all, my name is Takuya. I'm a technical leader from a tech organization based in San Jose, California. And today's session is about the details of ACI forwarding. So it's for the advanced users. So if you have not touched ACI before, or if you're not familiar with the ACI yet, then this session may be a little bit too much for you. But if you have a plan to actually use it in the near future, then I can guarantee you that this session will help you in that near future, even though you may not understand everything what I may say today. Okay? So this is today's agenda. First, we're going to start with the overlay VXLAN and TEP. So that's basically how ACI sends the traffic from one leaf to another. So that's basically the life of a packet in ACI Fabric. And after that session, I'm sure everybody is going to have a lot of questions. So demystify those questions. To demystify those questions, we move on to the next session to cover all the components related to the ACI forwarding. Then after that, we're going to move on to the ACI packet walk to see how we can apply the knowledge that we've learned so far. Okay? Then this is a WebEx team for this session. So this session being the advanced topic, so I have lots of contents to cover in this session. So if you guys can save your questions to the end of the session, that would be appreciated so that I can make sure we can complete the session within the time. And if you can ask the question in the WebEx team so that I can answer later, then that would be also appreciated. All right. So this one is acronyms and definition for your reference. And as you can see over there, there's a red bookmark. So during the session, if you see that mark on the slide, that means it's a reference slide. So I'm likely going to skip that slide because that's usually just a CLI reference or something. Okay? So with that said, let's start with the overlay VXLAN and TEP. So this is the basic ACI topology. We have leaves and spines, and then we have VRF overlay 1 to connect leaves and spines. That's the ACI infra VRF. We call it overlay 1. Then we have TEP addresses for all the leaves to represent themselves in that infra VRF. Tunnel endpoint IP. We have these TEP addresses for spines as well, but we don't really use it for forwarding. But instead, we use Anycast TEP address for spines that is shared across all the spines. So then, why do we do that only for spines? That's because at the end of the day, our purpose, our goal is basically send the traffic from one leaf to another. So we don't really care which spine actually does the forwarding in the middle. So that's why we use Anycast TEP address so that we can provide, any spines can provide the same functionality. All right? Then let's take a look at the really basic idea of how ACI sends the packet in the infra network with this example flow. So first, packet comes into the leaf. Then this packet needs to go to the leaf 2 in the middle. So it has to go through the ACI infra. In that case, we add another encapsulation with this blue outer header. In there, we have Ethernet, IP, and VXLAN header. And inside of that, we have the original packet. Once it reaches to the destination leaf, it will decapsulate the blue outer header, and then that destination leaf will do the rest of the forwarding. So that's the very basic idea, all right? So let's take a look at a little bit more closer, detailed look at each example. First scenario is source leaf knows the destination, and the destination is on the same leaf. The second one is source leaf knows the destination, and it's on another leaf. The next one is source leaf does not know the destination, and it somehow decided to do spine proxy. So what is spine proxy? Don't worry about it, we'll get there. Then the last one is source leaf does not know the destination, And instead of spine proxy, it decided to do flood. So let's start with the first one. In this case, the destination is on the same leaf. So it's really simple. No VX line encapsulation, no overlay one, because it completes within the single leaf. So there's nothing to talk about it in here. The main one is the next one. The destination is on another leaf. So in this case, let's say the packet comes in from leaf 1, and then leaf 1 knows the destination is on leaf 2. So in this case, we need to send the traffic to leaf 2. So we add the blue outer header. Then what's important in here is this outer IP address. So the source IP in the outer header is leaf 1 TIP address because it came from leaf 1. The destination is leaf 2 TIP address. So with these two information, we can send this traffic with this blue outer header from leaf 1 to leaf 2. Then, why do we need this VXLAN header information as well? As long as we have the source IP, destination IP, shouldn't that be enough to send the traffic? The answer is, for the forwarding scope, as it says in here, we keep VRF or bridge domain VNet information in there to keep the forwarding scope information across different nodes. When packet comes in to leaf 1 from, let's say, bridge domain 1, and then we are doing the switching on bridge domain 1, then we need to make sure the destination leaf also do the switching in the same bridge domain. We don't want this leaf 2 suddenly start switching in the completely different VRF or bridge domain. So that's why we keep the forwarding scope information in the VXLAN VNet format in this blue outer header. Okay? Then, once we get this, created this blue outer header, the packet physically leaves the leaf and then reaches to the spine first. Because in ACI, there is no leaf-to-leaf connection, no spines-to-spine. It always goes to spine first. Then, spine checks this outer header first. Then in this case, the destination IP is leaf 2 TIP address. So spine just sends it directly to leaf 2 without even looking at this inner header. So spine doesn't know what this packet actually is. It just sends it to leaf 2 only based on this outer header information in this scenario. So this anycast TIP address in here is not used in this scenario. Then when the packet reaches to this leaf 2 also checks the outer header first to make sure that the packet is destined to him. And then the destination is leaf 2, so that's why leaf 2 decides to decapsulate the packet and then checks the inner header information and then do the rest of the forwarding based on this leaf 2's information. Okay, so that's the scenario 2. Then the next one is source leaf does not know the destination and it decided to do the spine proxy. So what is spine proxy? In ACI, on the spine, we have a database called a COOP database. In that database, we store all the endpoint information of the entire ACI fabric. So if leaf doesn't know about the destination, then leaf just can ask spine so that spine can do the lookup for him. So that behavior itself is called spine proxy. Okay, so let's take a look at how the packet header will look like when we do this spine proxy. So packet comes into the leaf 1, same as the previous scenario, but in this case, we decided to do the spine proxy. And then still, it goes through the infra network, so we add the blue outer header like this. The difference is the destination IP header. This one. Previous scenario, we used leaf 2, but in this case, we use anycast TIP address because we need a spine to do the lookup. So once the spine receives this packet, it checks the destination outer header again, then it sees the anycast TIP address. So spine decides to look in the inside. Then based on that inside packet, we will do the lookup on the COOP database. Then in this case, spine knows the destination is on leaf 2. So how does the packet header after that look like? It will be like this. Destination IP will be leaf 2, of course, but the source IP, it's still leaf 1 because the fact that the packet came in originally is still leaf 1. It didn't change. Spine just did the proxy. So that's why it's still leaf 1. Then after that is pretty much same. Leaf 2 just checks the destination IP in the outer header, then it's himself, so it decapsulates it, and then do the rest of the forwarding based on the inner header information. Okay? The last one is it decided to do flood instead of spine proxy. So when we talk about the flood in ACI, we need to talk about the FTAG tree first. That is the mechanism to avoid loop in ACI. So this blue line is the FTAG tree in ACI. So we pick one spine as a root. Then from that one spine, we create a path to all the nodes that are physically connected to that spine. In this case, leaf 1, 2, and 3. Then we still have one node left in here. So in this case, leaf 3 created a path to the last node, last spine. It just happened to be leaf 3, but it doesn't have to be. It may be leaf 1 or leaf 3. And then in ACI, we have this tree, 16 of them, so that we can load balance the flood traffic equally. Because if you have only one of them, then these two links in the middle will never be used for the flood traffic, which is not efficient. So that's why we have 16 of them, 16 of this FTAG tree, so that we can equally load balance that flood traffic. Then by following this blue line, FTAG tree, we can make sure all the traffic will reach to the one node only once without any duplicate, without any loop. Okay? So then, how does the packet header look like when we do this flooding? Of course, we will add the blue outer header again. The difference is, again, this destination IP in the outer header. In this case, it's called a GPO. It's a group IP in the outer header. It's basically a multicast IP. Then where do we get that multicast IP? So when we first bring up the APIC controller, we need to configure some basic parameter first. And then one of those parameter is multicast IP range. And then when I first brought up the APIC, I had no idea what the multicast IP range is for. But that IP range is actually for this one. So APIC will automatically pick one multicast IP from that range and then assign it to each bridge domain. So each bridge domain has one multicast IP from that range. Then that IP address will be used in here so that we can tell this is the flood traffic within that bridge domain. Okay? Then we need one more information, which is FTAG tree ID, because we have 16 of them. So we need to make sure all the devices, all the nodes, leaf 1, spine, leaf 2, everybody needs to use the same FTAG tree. So to make sure, we include this FTAG tree ID in this GPO as well as the multicast IP of the bridge domain. So it's basically the combination of bridge domain multicast IP and FTAG ID. So if you take a look at the APIC GUI in the bridge domain section, we have the tab called Advanced. In there, you can check which multicast IP is used for the bridge domain. And then if you see that, you'll notice that the last 4 bits are always 0. That is because they are saved for FTAG tree ID. So by combining that bridge domain multicast IP and the 4 bits number for FTAG ID, we create this GPO. And then send the traffic to spine. Then spine will just check this outer header, then we'll follow the FTAG tree ID. Then it reaches to the leaf 2 and leaf 3. And in this case, the flood traffic is within the bridge domain 1 because it came in from bridge domain 1. So leaf 2 will decapsulate the packet and then do the rest of the flooding on this leaf choose bridge domain 1. But leaf 3, it doesn't have bridge domain 1, so it doesn't do anything. But it still have one last path of the F-tag tree in this case. So leaf 3 will send the traffic up to the last spine. In this particular example, it doesn't have any meaning. But let's say you have a multipod configuration set up. Then the multipod may be connected from this spine. Like IPN device may be connected from that spine to go to the another pod. So in that case, we need to make sure the flood traffic will reach to that last spine as well, so that the flood traffic can reach to the another pod as well. So that's the F-tag tree and the flood in ACI. So how do we pick which scenario to use for which packet? It's all based in the endpoint information. So let's take a look at the endpoint and then let's learn it. So in this section, we have endpoint, EPG, VLAN type in ACI, endpoint type, endpoint learning, and COOP database. So let's start with the endpoint itself. What is an endpoint in ACI? It's basically a combination of MAC address and /32 IP address. Maybe it's only MAC address, or maybe MAC address and more than one IP address, but basically it's a combination of it. Then in ACI, we store that combination as a single entry in endpoint table. So we don't have a MAC table in ACI. So then if we have endpoint table instead, how do we do the forwarding? What kind of things happen for the other forwarding table? So let's take a look at this left bottom table. In the legacy, we have routing table for all the IP information. We have MAC table for MAC address. We have ARP table for the relationship between MAC and /32 IP address. But in ACI, all those informations are combined in the endpoint table as a single entry. But we still have a routing table because this endpoint table is only for MAC address and /32 IP information. So all the other subnet information will still be in the routing table. So when we do the forwarding lookup in the ACI, what happens is we check the MAC address in the endpoint table first. Then, if it's a routing traffic, we check the same endpoint table for the /32 IP address. Then, if it's not there, we will check the routing table next. So that's how the forwarding happens in the ACI, the general idea. Then, what about the ARP table? In ACI, we use ARP as a protocol, but we just don't store that information in the ARP table. But there is an exception, like it's said in here. If it's L3 out, then it's supposed to be connected to the external router, where we would see tons of routes behind it. So if we do the same endpoint mechanism for L3 out, then we would likely end up with the one single MAC address of NextHop router and thousands of IP address /32 IP address on that single MAC address, which doesn't scale. So that's why we don't do that in the layer 3 out. But instead, we do exactly same thing as a normal router, only for the layer 3 out. So for layer 3 out, we store all those routing information in the routing table. Then we learn the MAC table, MAC address from the NextHop router, and then we still store the MAC address in the endpoint table, but without IP information. Then MAC address and NextHop IP relationship will be in the ARP table, only for the layer 3 out. So for layer 3 out, it's exactly same as a normal router. Okay? Then, what is the endpoint group? It's literally a group of endpoint. But in ACI, we can say endpoint group is a security domain. So that's why it's used to implement traffic filtering. In ACI, all the endpoints within the same EPG can talk to each other without any rule. But if we want to talk outside of the EPG, then we need a contract to explicitly allow it. So that's why EPG is a security domain. And in EPG, we have a VLAN. So why do we need a VLAN for security domain? How do we use it? It's just an identifier for the security domain. So we could call it just a label. So then what happens for the forwarding? Because in the legacy network, VLAN is the layer 2 forwarding domain. But in ACI, it's an identifier for EPG, security domain. So in ACI, layer 2 forwarding domain is a bridge domain instead of VLAN. Okay? And then if that's the routing traffic, then the routing domain is, of course, VRF. So that part itself is not changed, still same as the normal router. Only the difference is bridge domain is the layer 2 forwarding domain. VLAN is an identifier for EPG. We will talk more about the bridge domain itself later. So for now, let's take a look at how we check the endpoint. There are basically two methods. The first one, the top one, is from APIC GUI. So from there, we can see this EPG have this endpoints in this leaf. So it's a very good summary view. But that's not the endpoint table actually used for the forwarding. That's just a table for summary in the controller. So when you actually check or verify the forwarding, we need to check the real endpoint table on each node, which you can do from show endpoint in the Leaf CLI. Then, the very important point in ACI is to be able to understand this show endpoint output. Because without, if you try to operate the ACI without understanding the show endpoint output, that means that is equal to you try to operate your network devices without being able to understand MAC address table. That's unbelievable, right? So that's why we need to make sure we can correctly understand and interpret this show endpoint command. So to do that, we need to understand the VLAN types in ACI. That's a little bit tricky part in ACI. So in ACI, we have 3 IDs: Access Encrypt VLAN, Platform Independent VLAN, PI VLAN, and VXLAN ID. So let's start with the Access Encrypt VLAN. Let's say we have Access Encrypt VLAN 5. So this VLAN ID is what you configure on ACI and on external device. And then that is the VLAN on the wire. So we will talk to the external endpoint with this VLAN. But internally, this is just an identifier for this EPG. So we classify this endpoint to this EPG based on this VLAN information, Access Encrypt VLAN. In EPG, we may have more than one Access Encrypt VLAN, and it could be a VXLAN. So it could be like this. We may have another ID, Access Encrypt VLAN, for the same EPG. Then internally, we map these 2 Access Encrypt VLANs into PI VLAN. This is just an internal ID for this particular leaf to get the EPG information for that Access Encrypt VLAN. Then in here, we have one more PI VLAN for this leaf, which is on the bridge domain. This one. So then why do we need that? It's because, one, to get the bridge domain information, but second, that's the most important part, when we try to do the routing across the L2 domain, in a legacy network, we create the SVI to go across the VLAN, right? Then in ACI, if you talk about the VLAN in here, we may have more than one, and then maybe one of them is a VXLAN. So which ID are we going to use to create SVI? Even if it's mapped to PI VLAN, we have more than one. So we can't decide which one to use. So that's why we have one PI VLAN for bridge domain, L2 forwarding domain, to create the SVI. Okay? But again, this ID is only for this particular leaf. So the same mechanism happens on the another leaf, but the ID itself may be different. So let's take a look on the leaf 2. We have the same Access Encrypt VLAN for same EPG on leaf 2. Then, of course, the mapping to the PI VLAN happens in here as well. But as you can see in here, the PI VLAN value may be different than leaf 1. but the functionality is same. Okay? Then, when we do the actual forwarding across nodes, then we need to have a shared ID. So for that purpose, we have VXLAN ID, which we talked about in the introduction section, right? So first, we map the access Inca VLAN to VXLAN ID as well. But those are not really used because those are basically an ID for the security domain. There are some exceptions like spanning tree BPDU, but most of the cases we don't use this VXLAN ID for forwarding. But instead, we use this bridge domain VXLAN ID for L2 switching. Then we use VRF for routing, of course. So that's the three basic ID in the ACI. Accessing a VLAN to communicate with the external device. PI VLAN, that's an internal ID only for that leaf to get the EPG and bridge domain information. Then VXLAN ID is for the forwarding. Okay? So with that information, we can now read show endpoint command. So this number on the left is PI VLAN. So that will tell you which EPG this is. Then we can also check this access Inca VLAN that is used on the wire. And then those are the IP and MAC address for this endpoint. Then the most tricky part is this show VLAN command. This is the command that everybody is familiar with. But in ACI, this ID is not the actual VLAN ID on the wire. It's the PI VLAN, as you can see in here. So please don't get confused with that. That's the PI VLAN.
What's PI stand for?
Platform independent VLAN. It's only for that platform, only for that internal. So then, if you add the extended option in here, then you can see that access Inca VLAN mapping to that PI VLAN as well. All right? And then this is another reference command to check more details. Then, now we know the VLAN types in ACI. So let's learn endpoint types as well. There are 4 of them. The first one is physical local endpoint. So this endpoint is physically learned locally on this leaf. So that's why it's physical local endpoint. That's the most basic endpoint in ACI. Then, virtual local endpoint. That is still local to this leaf, but it's behind Cisco virtual switch, virtual leaf, like Cisco AVS or AVE. But it's still local to the leaf. So that's why it's called virtual local endpoint. The next one is remote endpoint. So that's the endpoint on another leaf. So from this leaf perspective, this endpoint is remote endpoint. But from this leaf in the middle, that guy's perspective, that endpoint in the middle is a local. So it's all perspective of each node. Okay? Then the last one is on-peer endpoint. So in this case, this endpoint is on another leaf, but that another leaf is a VPC peer of this leaf. So that one is specifically called on-peer endpoint. But what's important in here is local endpoint and remote endpoint. Because this endpoint concept is new in ACI, so we need to learn how we learn these endpoints. And then the way we learn the endpoint is different if it's local or if it's remote. So let's take a look at how we learn those endpoints. First one is the local endpoint. So this is the most basic and most important endpoint. So that's why we have the MAC and IP as a single entry, like we mentioned at first. And then if this MAC address has more than one IP address, then we will see next line in here, and then it says maybe IP address 52. But that's still one single entry. Then how do we learn it? For the MAC address, it's still same as the legacy switches. Packet comes in, then we can just check the source MAC address, and then we learn it from data plane. So it's same. But the point is, the packet has to come from the front panel port. If the packet came in from spine, then it's not local. So for it to be local MAC address for local endpoint, it has to come from front panel port. Then we learn the MAC address from that traffic as a local endpoint. What about the IP address? That's the difference between ACI and the normal switches. We learn IP address from data plane as well. So how do we do that? We have two scenarios. The first one is this one. If the packet comes in from front panel port, again, it has to be front panel port. If it's from spine, it's not local. Then packet comes in from front panel port, then if that packet is a routed traffic, then we learn MAC and IP at the same time from that same packet from data plane. Okay? Then the next scenario is ARP request. If the ARP request comes in from front panel port, then we will check the ARP header, and then we will learn both MAC and IP from sender MAC and the sender IP in the ARP header from data plane. So we don't use any CPU resources or anything. We just learn it from data plane. So this feature or function is really powerful because when endpoint moves from one point to another, then we don't have to wait for that endpoint to let the network device know about its movement by sending the GARP or something. We just immediately pick it up. We just immediately pick it up. As soon as this endpoint that moved starts sending the traffic. So that's really powerful, but at the same time, it's really sensitive because it picks it up immediately. So we need to be careful when we design the ACI with this endpoint learning. So we need to learn how that endpoint learning, especially IP learning, happens in the ACI before we design the ACI or we use that ACI in the production network. Okay? Then, local endpoint is not the only endpoint. We need to learn how we learn the remote endpoint as well. Remote endpoint is a cache information because technically we don't need it. We can still function without this one. As long as we have local endpoint, then if that leaf doesn't know about the destination, we can just ask spine. So that's why this remote endpoint is a cache information to optimize the traffic flow. So that's why we keep these information minimum. So that's why we store these MAC and IP separately. Because if the traffic is switching traffic, then we only need MAC address. If it's a routing traffic, then we only need IP address so that we can just send it to another leaf. So that's why we keep it separate to keep the information on that leaf minimum. So then how do we learn them? It's still from data plane. So when the packet comes in from spine, then it's a remote endpoint. Then we learn either MAC or IP. So how do we decide if we learn MAC or IP? It's based on the VXLAN header in that packet. When the packet comes in from spine to the leaf, then it should have the VXLAN header. And in there, if it's the bridge domain VNet, then that means that traffic is a switching traffic. So we learn only MAC address. If the traffic from spine has VRF VNet, then it's a routed traffic. So we learn IP address only from that traffic. But both of them happens from a data plane. Okay? So that's how we learn the remote endpoint. Then in the remote endpoint, it always points to the tonal interface because it needs to point to the another leaf. So this is the command to check which tonal interface is pointed to which node. Okay? Then the last thing is COOP database. This is basically a endpoint table in the spine. Then how does the spine learn these information? Spine doesn't learn anything from data plane. It's a responsibility of each leaf. So when leaf learns a local endpoint, it will report that information to spine so that spine can store that information. But let's say leaf learns a remote endpoint, then that information is not reported to spine because remote endpoint is again just a cache information. So spine only stores the local information that is reported from each leaf. Then spine usually never push that information to another leaf, because if that leaf doesn't know about it, they can just ask spine. The only one exception is when the endpoint moved. When endpoint moved from one location to another, then this new leaf will report that endpoint as a new local endpoint to spine. Then spine will notice that that endpoint moved from this leaf to another leaf. So that time is the only time spine let only this leaf know about the endpoint movement to tell them that that endpoint is no longer with you. But other than that, spine never tells that information to leaf because we have to use the spine proxy. Okay? Then, for that endpoint move scenario, we have a hidden slide about the bounce entry. That behavior is called bounce entry. So if you'd like to know about details about the bounce entry, please check that hidden slide. That should be in the PDF that you can download from Cisco Live website. So now, let's move on to the bridge domain and VRF. We learned the overview and endpoint learning. So now the time to learn about the forwarding domain. All right? So in this section, we have pervasive gateway and forwarding scope and forwarding mode in bridge domain. So this is the pervasive gateway. That is basically what you configure as a subnet in the bridge domain. So when you configure pervasive gateway, you can check this show IP route command to see what you have on that particular leaf. So the first one is the subnet, which says pervasive in this label. So you can tell that subnet is the bridge domain subnet that we configured. And the second one is /32. That's an exception for this routing table. We still have /32 information in the routing table, but that is because that's not the endpoint. That's the SVI IP for this pervasive gateway. Okay? Then I have some explanation in here, but let's skip it and then jump into the example for now. So let's take a look at this blue bridge domain. As we saw before, we create one PI VLAN for bridge domain to create the SVI. So if you configure more than one subnet under the bridge domain, we will have a secondary IP address on that same SVI. So this first pervasive gateway will be the primary IP on the PI VLAN SVI. This second IP will be the secondary IP on the PI VLAN SVI. And then what's important in here is how we deploy these pervasive gateways. So as you can see, this blue bridge domain has these 4 endpoints, and then they are on leaf 1, 2, and 3. So that's why we install this pervasive route information only on leaf 1, 2, and 3, not 4 and 5. Same thing applies to pink and green bridge domain. They only have resources on leaf 5, so that's why we only install that pervasive gateway information on leaf 5. Then things change when we configure a contract. Let's say we configure a contract between endpoint C and endpoint E. Then what happens is we exchange the pervasive route information. So these VRF on leaf 1, 2, 3 will have a pink pervasive route information. And then same thing happens on the another one. It will now have blue pervasive subnet information because we know that somebody in this bridge domain wants to talk to this pink bridge domain. But then, why do we need that in the first place? Because if leaf does not know about the destination endpoint, we should be able to ask spine to do the spine proxy. So why do we have this pervasive route information? The answer is, to perform spine proxy, we need pervasive route. So let's take a look at this example. In this case, we want to talk from this endpoint C to this pink endpoint, 5001. And then let's say this leaf doesn't have endpoint information for 5001. In this case, it's a remote endpoint because it's on another leaf. So this leaf doesn't have a remote endpoint for 5001. Then, from a forwarding perspective, forwarding lookup perspective, first we check the endpoint table. Then if we don't have an endpoint in the endpoint table, then we check the routing table next. Then, let's say we don't have the pervasive routing here, but instead we have a L3 out that's advertising the default route into the ACI. Then we will hit that default route instead of going to the spine proxy. So to avoid that, we need to make sure to specifically have an entry in routing table to let leaf know that we need to do spine proxy for this subnet. So that's why we install pervasive route, so that we can perform, specifically, explicitly perform the spine proxy. Okay? And then in case you are interested in details, we have one more hidden slide after this to show you how show IP route command look like when we have the contract between two bridge domain and when we don't. And then it will show you how the pervasive route actually look like. So in case you are interested in, please check that out. So now, let's move on to the forwarding scope. So this is a really confusing point for the beginners, because in ACI, we store MAC and IP as a single entry in an endpoint table. So some people wonder, do we use IP information to do the switching as well? Let's say packet comes in, and then it has Ethernet and IP header. Then we have endpoint information which has both MAC and IP. Even though it's a switching traffic, we have IP header and IP information in the endpoint table as well. So do we break the rule of the switching and routing and then use that IP to look up only for the ACI? We don't do that. So we still follow the normal switching and routing behavior. Only the difference is how we store it. So in the endpoint table, we store MAC and IP in the single entry, but with respective forwarding scope. So in a single entry, we have MAC and IP, but at the same time, this MAC has one scope for the bridge domain. And then this IP has a scope, VRF scope, for that IP address. So in this table, to make it easier to look, I split that one single endpoint in two different entries. So let's say for this information for endpoint A, it has MAC address 1111 and then IP address of 0.1. So if you look at the endpoint itself, then those two entries is in a single entry with a different VNID. So I just split up in each bridge domain VNID and VRF VNID so that it's easier to see. So when we do the forwarding happens based on the bridge domain VNID first, then move on to the VRF VNID, even though those two informations are stored in a single entry. Okay? So let's take a look at the exact examples. So let's start with the endpoint A to endpoint B. In this case, it's same EPG, same subnet, same bridge domain, same VRF. So the packet from endpoint A should be sent to MAC address 2222. Then what happens is we check MAC address 2222 in bridge domain VNID. Then we see that entry pointing to endpoint B. So we do the switching. Then what about the endpoint A to endpoint C? It's two different EPGs, but still it's the same subnet in the same bridge domain. So in this case, from endpoint A's perspective, it will send it directly to MAC address 3. So ACI will just check the bridge domain VNID entries with MAC address 333, which is there. So we do the switching based on that MAC address. Then what about the next one? That is the tricky one. Two different EPGs, but it's in the same bridge domain, same layer 2 forwarding domain, but they are in two different subnets. So in that case, from endpoint A's perspective, it's still sending the traffic outside of the subnet. So then endpoint A's perspective, where do we send the packet to? That's the network 101, right? If it's the outside of the subnet, we send it to the default gateway. So in this case, the default gateway is ACI Fabric, pervasive gateway. So the packet from endpoint A will be MAC address of pervasive gateway MAC, ACI bridge domain MAC address, destination IP of this final destination, 1.1. So what happens in the ACI is we check the destination MAC address first, then we notice that it is the bridge domain gateway MAC address. So that's the first time we check the IP information for that packet because we need to do the routing because it sent it to the default gateway. So then that's the first time we check the VRF VNet tables and then check the IP address. Then it happens to be in the same bridge domain. The destination happens to be in the same bridge domain. But we still do the routing. And then send it back to the same bridge domain, EPG3, to this endpoint D. So please don't get confused that even though these two endpoints are in the same bridge domain, we still do the routing based on the IP if it's two different subnets. Okay? Then the next one is two different bridge domain. So in this case, of course, it's a different subnet, different L2 forwarding domain, so it's simple. Just do the normal routing with the default gateway. Okay? So what I wanted to emphasize in that is in ACI, we store the MAC and IP information in a little bit different way, but we still follow the normal forwarding behavior. We didn't break it. We still do the same thing. Okay? So that's why it's really important to learn how we store, how we learn the endpoint information. Because anything else will be basically same. Okay? Then let's check out the forwarding option in the bridge domain. Because I just said basically everything else is same. We follow the normal forwarding behavior, but we have a way to change it. So, but change as in a good way. We can optimize it. So these 5 options are the options to optimize the traffic a little bit. In the bridge domain, we have a lot more options, but other than these 5, most of them are related to the endpoint learning. So for those options, I highly recommend you guys to check this Endpoint Fabric Endpoint Learning white paper. That is a very good document. At least I think it's good because I wrote it. So I hope you guys like it too. All right. So let's start with the unicast routing. So if you disable the unicast routing in the bridge domain 1, then what happens is we stop learning the IP information in that bridge domain, and also we kill the pervasive gateway information. So that's why we delete this pervasive gateway MAC entry in here and all the IP information related to this bridge domain. So this bridge domain 1 will be the pure layer 2. No routing happens in there. No IP learning happens there. But bridge domain 2 still have unicast routing on. So that's why even though it's in the same VRF, it still have the IP information for bridge domain 2 in this VRF 1. So it's per bridge domain. Okay? Then the next one is ARP flooding. If the ARP flooding is enabled, then we will do basically the same thing as a normal switch. When we receive the ARP request, we flood ARP request within the L2 flooding domain. In ACI, it's bridge domain, so that's slightly different, but we flood within the L2 flooding domain. That fact is same as the normal switch. Then, when we disable the ARP flooding option, what happens is when we receive ARP request, we check the ARP header and then check the target IP. Then instead of doing the flood, we will do the routing based on that IP information. So what happens is packet comes in, then it's ARP request, ARP flooding is off. We check the target IP in the ARP header. then first we check the endpoint table for that IP address. And if it's there, we directly send it to that destination. But if it's not there in the endpoint table, we move on to the routing table. Endpoint table and routing table, it's always that two steps. Then in the routing table, if it's the ACI endpoint, we should have the pervasive route information, right? The one that we just mentioned. Then the pervasive route should point it to the spine proxy. So that's why we do the spine proxy if we don't know about that target IP. So that's the op flooding off. Then when spine receives it, spine will just send it to the destination based on the COOP database. And one key point is, if spine doesn't know about that destination IP either, then what happens is spine drops it first. And then after that, spine will try to detect it because it might be a silent host that we just don't know yet. So that behavior is called op-glean or silent host detection. And we'll talk about it on more details in a later section. So please stay tuned. Then the next one is L2 NO unicast. We have two options for this one as well, flood or hardware proxy. If it's flood, we do the same thing as a normal switch. So first, we receive the packet, we check the destination MAC always. Then, if that destination MAC is not learned on ACI endpoint table, then that's unknown. So then we will follow this option. Either we flood or do hardware proxy. If it's flood, we just flood within the bridge domain. So it's same as the normal switch. Normal switch receives the traffic, check the MAC address, and then the MAC address is not in the MAC address table, we flood within the VLAN, right? So we do the same thing in the bridge domain. If hardware proxy is used, then we check the MAC address table. We don't have MAC address table in ACI. So we check the endpoint table, then MAC address is not there, then we don't have any other tables to check next, like IP table. So in that case, we directly go to the spine proxy, if it's set to this one. Okay? Then once spine receives it, spine forwards it based on the COOP database. But if COOP database doesn't have that either, then what happens is, like the previous one, we drop it, and then we don't do nothing after that. Because it's not an IP address, so we can't do ARP for MAC address. So that's why we don't do our silent host detection for the MAC address. So if you have like a really sensitive L2 host, or maybe a silent L2 host, then it's recommended to have a flood option because we can't detect it if it's a silent. Okay? Then the next one is L3 unknown multicast. The name is tricky, but this is basically for IGMP snooping. So when the L2 multicast traffic comes in, we check the multicast IP in the IGMP snooping table. And then if we have an entry in that IGMP snooping table, we just send it to the receiver, right? Then if you don't have that multicast group in the IGMP snooping table, then we follow this behavior. So we still check the multicast IP even for the IGMP snooping. That's why the name is called L3 unknown multicast flooding. But it's not about the multicast routing. It's for the IGMP snooping. Okay? So if it's set to flood, and then multicast IP is not in the IGMP snooping table, we flood. But in the first generation leaf, it's not really a flood. We do flood on the ingress leaf and only on the leaf that has IGMP querier. But that behavior is fixed on the second generation. The difference between first and second generation, we will have another whole section for it, so please wait for that one. Then if you set it to optimized multicast flood, then we will send it only to the IGMP querier. All right? The next one is multi-destination flooding. So this is basically a catch-all for the other protocols that was not covered by the previous options, like ARP request or L2 unicast or IGMP snipping, those other traffic that were not covered by those options will fall under this one. By default, we will flood it in the bridge domain. And then if you want to reduce the flooding domain, we can set it to the flooding encapsulation so that we can just flood within the access encap VLAN. We can also drop it as well. For the flooding encapsulation option, we changed the behavior a little bit in release 3.1. So if you'd like to know details, then again, there's another hidden slide after this. So please check that one out. Okay? Then, now we know the endpoint learning. Sorry, could I take the question at the end of the session? Thank you. Then we learn the endpoint learning, bridge domain, and VRF forwarding scope. So let's learn ACI specific component, spine proxy, and ARP glean. So this is the spine proxy flowchart. The red line is the scenario where we do the spine proxy. But this is basically a recap for what we just talked. So for the L2 traffic, packet comes in and it's L2 traffic. So we check the destination MAC in the endpoint table, and then we decide to do flood or spine proxy based on this option, right? Then if it's layer 3 or the up flooding is off, then we follow this right direction. And then basically we check the routing table for the pervasive route. Then if we have it, we do the spine proxy. Okay? For the other scenarios, please check that one out later to get the better understanding for the another scenario. Okay? Then now, the ARP glean, silent host detection. Okay? Like we mentioned, L2 traffic, we can't do it, so we just drop it. So please be careful when you have a L2 silent host. But for L3 traffic, we can do ARP glean. So let's take a look at how we do that. So first, packet comes in, and then this is the IP traffic, routing traffic, okay? So we hit the pervasive route to do the spine proxy. Then we send it to the spine. Then we hit the anycast step address, so spine decides to do the COOP database lookup. But we don't have a COOP database entry in here, in this case. So we drop it first. Then after that, spine will generate a new packet. That is called ARP glean. And then that is sent to all the leaves. And then all the leaves will check their bridge domain subnet to see if they have a mapping subnet for that unknown IP. Then if they have it, each leaf will generate ARP request from their own bridge domain SVI and then send it down to that bridge domain in their leaf. But for the leaves that doesn't have a mapping subnet, then it doesn't do anything because there's no need for him to do anything. So that's how we learn how we detect the silent host, by creating the ARP request from the leaf itself. Okay? Then the next section is forwarding software architecture and ASIC generation. So it may be a little bit too much just to operate the ACI, but I like those details of the product. So if you guys like it, I hope you guys like it too. So the top layer is the APIC, and then the middle layer is leaf supervisor process, and then the bottom one is the leaf line card process. In the ACI leaf, it's a one-box switch, but internally it still has supervisor process and a line card process, even though it's physically in the same box. Okay? Then let's talk about the endpoint learning processes. We create EPG first, then under that, we have endpoint manager process on supervisor level. Then we have endpoint manager client on leaf line card process. And then they will use HAL, hardware abstraction layer, to talk to the ASIC so that we can install the entry on the ASIC. But in this case, it's about the endpoint. So we learn endpoint information from hardware. So the direction will be actually from bottom to top. ASIC will learn it from data plane, and it will tell that information to software, EPMC. EPMC will tell that to EPM. The EPM will tell that information to Spine COOP database, and also it will tell that information to APIC as well, so that from APIC we can check the summary view. Okay? Then, what about the routing table information? APIC component will be bridge domain or L3 out. Bridge domain will create the pervasive route information. Then L3 out will create the static route or the routing protocol information. Then we store that information in the routing table, which is excuse me, which is handled by unicast routing information base URIB process. Then that guy will talk to UFIB forwarding information base process on the line card, and then that guy will install that entry to the ASIC through HAL. Then the last one is about the contract. So contract is not really the scope of this session, but let's just quickly take a look because it's basically do the same thing from a layer wise. So we create the contract, and then we talk to the policy manager process on the leaf, and that guy will talk to the ACLQoS policy on the line card level, and then by using HAL, we install that information into ASIC. So if you are interested in checking more details by yourself, I have some reference syntax, CLI syntax for each process. So you can check those syntax to see what each process actually does or what kind of information each process has. All right? Then the next one is leaf ASIC generation. We basically have first and second or later. In the first generation, we had two ASICs. One of them is Broadcom chip, another one is Cisco ASIC. Most of the functionality is on Cisco ASIC, this one. And then in there, we have two different types of block. GST, Global Station Table, and LST, Local Station Table. And then we have that set of tables for both ingress from leaf to spine and egress from spine to outside. So we have that set of table for each direction. In total, we have 4 of them. But the downside of this one is we have some duplicated information in each table. But that's how the ASIC worked, so we had to keep the 2 or 4 different tables even though there are some overlapping information. So that was not really efficient. So in the second generation ASIC, we only have one gigantic ASIC, and that's it. And then inside of that, we don't have GST or LST, but instead, we have FP tiles, forwarding policy tiles, and then a lot more than 4. And also each tile's capacity is a lot more than the previous one. And then the best part is, we can use it for both ingress and egress direction. So we don't have to duplicate the information. So from capacity-wise, efficiency-wise, it's much better. And also the flexibility, not a lot of customer does it, but we can carve those FP tiles usage into based on your requirement. If you want more IP entries, then you can do IP weighted mode. It's not that name, but we can do the different carving based on your requirement for your capacity. So that's really flexible, and then we didn't have that feature in the first generation. So the second generation has more scalability, efficiency, and flexibility. And also, it has a much better debuggability as well. All right? Then, spine ASIC generation. So in the first generation, in the line card, we have Cisco ASIC, and then fabric card, we had Broadcom chip. So let's talk about the each functionality. On the line card, it usually checks the TEP information because line card is the first one who receives the packet from leaf. So it needs to check the destination outer header. Then it needs to decide if it's the spine proxy or to the another leaf. Then after it decides that information, it get that information, it will send it to fabric card. And then if that was the spine proxy traffic, we will do the COOP database lookup in the fabric card. If that was not the spine proxy, then we don't do much in the fabric card. Fabric card will just send it back to the line card where the destination leaf is connected to. But it still always go back to fabric card. Okay? In the second generation, the line card and the fabric card functionality is same. It's exactly same. But only the difference is this ASIC. Even in the fabric card, now we have Cisco ASIC. But other than that, it's pretty much same. Okay? So now we learned all the forwarding components in the ACI. So let's take a look at the packet walk to see how we can apply those knowledge. So this is the topology for this example. The left side is a logical topology. We have two endpoints, endpoint A and endpoint B, in two different EPGs and two different subnets. But it's in the same bridge domain. So that was the, one of the tricky scenarios that we mentioned earlier. Then the physical topology will be like this. Endpoint A is on leaf 1, endpoint B is on leaf 2, and then nobody has any information about each other yet. Okay? Even the endpoint, it doesn't have anything yet. All right? So what happens first when we want to ping from endpoint A to endpoint B? What happens first is endpoint A is trying to resolve the default gateway because, all right? Because the endpoint A, from endpoint A's perspective, endpoint B is outside of the subnet. So again, that's why we have to send it to the default gateway. So let's resolve the default gateway first. So in this case, endpoint A will send that ARP request to leaf pervasive gateway. So from that ARP request, leaf 1 will learn the endpoint A's information from data plane. It learns both MAC and IP at the same time from this single packet. Okay? And then that's the local endpoint. So that's why leaf 1 will report that information to spine. So with this single packet, leaf 1 in spine COOP database has endpoint A's MAC and IP information. Okay? And then leaf 1 will reply, and then endpoint A will get the default gateway information. And after that, endpoint A can finally send the ICMP to IP address of 1.1 and then the destination MAC address of default gateway. Okay? Then leaf 1 will check the MAC address first in the endpoint table. And it's the default gateway. So that's why we decide to do the IP lookup in the endpoint table first. And then that's the endpoint table of this leaf 1. And we don't have IP address 1.1 yet. So that's why we move on to the routing table. And in the routing table, we have pervasive route for 1.1 IP. So that's why we decided to do the spine proxy. Then send it to spine. Then spine will check the COOP database. And then this is the COOP database. And as you can see, it doesn't have 1.1 IP yet. Okay? So that's why it will drop it. But what happens after that? Exactly. So spine will send the ARP glean. Then leaf 1 and leaf 2 will check the bridge domain subnet for the unknown IP, in this case 1.1. And then both of them have bridge domain for that one. So that's why both of them will create the ARP request from the bridge domain SVI of each leaf. Then in this case, 1.1 is leaf 2, is on leaf 2. So endpoint B will just reply. And then from that reply, leaf 2 will learn endpoint B's information. And then this is a local endpoint from leaf 2's perspective. So that's why leaf 2 will let spine know about that new endpoint. So based on that information, we can have endpoint B information in the COOP database and endpoint B information in the leaf 2 endpoint table, both MAC and IP. Then what happens next is endpoint A will send the second ICMP because the first one was already dropped on the spine. So the second ICMP, the packet parameter will be same. Default destination MAC address is the default gateway. Destination IP address is 1.1. Then leaf 1 does exactly same thing again. It checks the MAC address. It's the pervasive gateway. So it checks the IP information in the endpoint table first. Then again, it still doesn't have it. So check the routing table, pervasive route, do the spine proxy, then spine check the COOP database. And now we have 1.1 in the COOP database. So spine can send it to leaf 2, finally. Then when packet reaches to spine leaf 2 from spine, then what happens is remote endpoint learning. Because it came from spine, so that's why we do remote endpoint learning. Then in this case, we learn IP address. Why do we learn IP address instead of MAC address? Exactly. I think everybody got it, so that's great. So based on that VXN ID, we know that this traffic is the routing traffic. So that's why we learn only IP address. Then this leaf 2 will check the internal header, inner header, and then check the endpoint B's, the leaf 2's endpoint table, this one. Then the destination is 1.1, which is there. So leaf 2 can send the traffic down to that endpoint. Then endpoint B will try to reply. But endpoint B still didn't have the ARP table for the default gateway yet. So it will resolve the default gateway, so send the ARP request, and leaf 2 will receive it. But at that time, leaf 2 will not learn anything because we already have this 1.1 and the 2.2.2 IP information, MAC information for that endpoint. So no new learning happens because we already know it. So it just reply. Then endpoint B will get the default gateway information. Then it will send the ICMP reply. Then again, destination MAC is default gateway. Destination IP is, this time, 0.1. So what happens is we will do the IP lookup in the endpoint table of leaf 2, which is this one. Then what's difference from previous scenario or previous flow is this remote endpoint. It's already there. So we hit this 0.1 entry in the endpoint table. So we don't have to check the routing table this time. We can send it to leaf 1 directly. Okay? Then let's say this is the endpoint A and endpoint B, and then those are in the 2 different APGs, right? So if you don't care about the contract, then yeah, we can just send it. But if you care about the contract, then this leaf already knows that the destination is this guy, and then on this leaf, and then in this case, EPG information is also there. So it knows the destination is on another EPG. So this leaf can apply the contract based on that information without sending it to the destination leaf. So what's good about that is we can technically drop the traffic in here if it's not appropriate, instead of using the bandwidth on this leaf spine and the spine leaf. So that's the benefit of having a remote endpoint. We can technically get rid of it entirely and then do always spine proxy, but if that happens, we always apply the contract on egress, even though we could know that traffic should be dropped in the ingress leaf. So that's one benefit of the remote endpoint. Okay? Then in this case, we have the remote endpoint, so send it to directly to leaf 1. The TEP address will be leaf 1, so spine receives it, but it doesn't do any inner lookup. It just checks the outer header, then it just sends it to leaf 1. Then when leaf 1 receives it, it will learn the endpoint B's IP address as a remote endpoint again, because it has VRF VNet in that. So that's why we learn IP instead of MAC. Then after that, leaf 1 will check his endpoint table for the destination IP. Then we will send it down to the endpoint. So now, finally, the ICMP worked in the ACI. So I hope everybody got the how ICMP work in ACI from no tables situations, like from the scratch. Then, if you'd like to know more details, if you'd like to verify even more details, then you can use this ELAM assistant. If you guys have worked in the, yes?
I'm just wondering, are you going to cover the actual the way the traffic forwards between the leaf and the spines and then ECMP, if possible, uploading on the VXLAN at all?
I can cover that after this session, but that's not in the slide. So if you'd like to know, please come to me later. I can answer that later. So then, if you have worked with the TAC engineer before on ACI, I'm sure they performed ELAM for you to do the ASIC level packet capture. But with this tool, you can actually do that by yourself. Without this tool, you have to know which ASIC is for what, and then which ASIC is like which generation, and what syntax is used, or how to decode that output. But with this tool, we can just punch in the IP address or MAC address, and then we can trigger the ACI ELAM. Then once it's triggered, we can check the report. It will automatically decode it for you, and then it will tell you this packet is sent out from Ethernet 115, which is member of port channel 1, and it will also tell you this is from EPG this one to EPG this one, and then it's trimmed, but in the original output, it will tell you the EPG name as well. So with this tool, you can actually say, we don't need TAC engineer. I'm actually better than you, if you'd like. All right, so if you'd like, please download it from the App Center, and then please check it. It's free, of course. All right, so that completes my session, and we still have some time. So do you guys have any questions? Yes?
Back on slide 99, when the traffic was going just there, that's it, 2 leaf 1 come up. What would be the source and destination MAC addresses of the outer encapsulation, the VXLAN encapsulation between leaf to leaf?
So the question is, when the packet reaches from leaf 2 to leaf 1, we have the outer header, and then what is the MAC address of that outer header?
Yes.
So that one is, we use the reserved MAC address. We have the 000C, 0C, to represent all the leaf node, and 000D, 0D, 0D to represent all the spines. So whenever we send the traffic from leaf to spine, the outer Ethernet MAC address is always 0C to 0D, and then when spine sends it, exactly. So
Just like a route will be routed to the spine and then back out.
exactly. So that's why we don't have to care about the MAC address details in the outer header, because it's always either C or D.
Okay. Now, what about the inner header?
The inner header will be, if it's the, yes. So the question is, so the outer header will be either 0C or 0D. What about the inner header? Inner header's MAC address. If it's the switching traffic, then we will keep the original MAC address information because we have to use it in the destination leaf. Then, if it's the routing traffic, then we already know that the destination MAC is for us, for pervasive gateway, so we need to perform the routing. So in that case, the destination MAC, the MAC address information in the inner header will also be 0C because we don't need it on the destination leaf. Right. So the pack.
It will be the leaf MAC address.
Yes. Exactly.
And the source MAC address will be also 0C because it's coming from a leaf.
Exactly. So that's why if it's a routing traffic, we only learn the IP information from the inner header because inner header may not have the MAC address of the original one. And then we don't need it. Yes?
I've seen in some documentations that multi-destination flooding
Mm-hmm.
is disabled when you are connecting active standby firewalls like HA. Is there any?
I don't think I have heard of that one. Maybe we can drill down the specific scenario later. But the multi-destination flooding is either flood in bridge domain or flood in encapsulation or drop. And then when we have the like active standby or firewall in two different pods, yeah, those are typical scenario. But there's no consideration regarding the that scenario and this option. So,
You do GOP or something, because they silent us, they don't talk.
sorry?
You just need to GOP, because they silent, they don't talk.
Yes,
So that's anything you do, you just need to gratuitous off to find if it does fail.
that's true. When the firewall failed over from one point to another one, from active to standby in the ACI, and technically, usually the standby firewall send the GARP so that we can detect it. But if the firewall started sending the routing traffic or ARP request, then we don't have to wait for the GARP because we can immediately detect that from the data plan as well. So, but that doesn't involve these options. So probably what you heard or what you read might be slightly different. So we can talk about the details later. Do you guys have any other questions? Yes?
What does the GARP-based detection option do?
So the question is, what is the GARP-based detection in the ACI, which was not covered in this session, but we have a specific option called GARP detection in the bridge domain. So what does it do? So basically, we don't need it for the newer generation leaves, but we used to have it because in the older generation leaf, we couldn't detect the IP move on the same interface on the IP move between two MAC address on the same interface. So when the IP of VMA moved to IP A is on the VMA with MAC address A. And then that IP moved to VMB with MAC address B. But from ACI perspective, both of them is learned on the same interface.
Same ESXi host.
Exactly. So in that case, even though IP moved from MAC A to MAC B, we couldn't detect it if it was a GARP. And then that was the limitation in the first generation ASIC. So to work around it, we did some software trick to work around it. So that's why we had that option. But in a newer generation, we don't really need it.
Do you need it with like the virtual IP option or getting or simple data plane learning?
To use the GARP-based detection? So the question is, do we need to like enable the another options to use the GARP-based detection? The answer is technically no, but there is, I don't remember if that was ARP flooding or not, but I think it was ARP flooding. Right. Yes. If ARP flooding was not, I forgot if it was enabled or disabled, but if it was, right. So if it was disabled, then the GARP-based detection option doesn't even show up in the GUI. Is there any other question? Yes?
I saw in some earlier slides they used to talk about detecting IP addresses through DHCP requests as well. Would you admit that? Has that never happened, or can that still happen as well?
The DHCP, so sorry, can you elaborate it again?
Okay. These say you can learn, a leaf could learn an IP address from an IP packet, from an ARP packet, and from a DHCP request packet.
I see. So
Is option 3 really true?
I don't think so. I don't know where you heard it, but
Now I've got an early stack of slides. It's got to be.
if the DHCP request is for some reason routed because of, let's say, on DHCP relay or something, then maybe. But if the DHCP relay happens, then
Take that out of my slides.
right. So in summary, we don't have any specific mechanism to learn IP from the DHCP request. There is some corner case where we could learn it, but there's no specific implementation specifically for DHCP.
Anyone else?
If nobody else had it, then yes, please.
Okay, last one. You mentioned that in case of a VPC, when an endpoint moves, in case of an endpoint moving, that the spine would report to the original leaf that the endpoint has moved, right?
Mhm.
Is that COOP or is that a different protocol, or how does that report
So the
happen? Or is it like a GARP?
So the question is, when endpoint moved from one point to different place, spine will let the old leaf know about it. So how does that happen? Is that the question?
Yeah, that's right. Does it
Okay.
sound like a gleaning up? Or
So that happens based on the COOP message. Because
is a COOP message from the spine to the leaf?
exactly. So in a normal situation, so let me repeat the question again just in case. The question is, when the endpoint moves from one place to another, spine will let the old leaf know about that movement, which is the exception of spine let the leaf know about the COOP database. And then how does the spine actually do it? The answer is based on the COOP mechanism. Then when we talk about the COOP database, we always talk only on the spine because the entire COOP database, the real database, is only on the spine. But the COOP process itself is running on the leaf as well. Because when we let spine know about the new endpoint, leaf EPM, I think there's a slide for that one, right? So this one, leaf EPM, this guy will actually talk to the COOP process internally on the same leaf. And then that COOP process on the leaf will let spine know, let COOP database on the spine know. So we do the same mechanism when spine tells leaf about it. Spine's COOP process will talk to the leaf COOP process. And then leaf COOP process report it back to the EPM process.
That's different again from some earlier slides that used to talk about.
If you can let me know about that slide later, I can double confirm it. But I'm fairly certain that is the case. Yes?
When you disable endpoint data plane learning on the VD, how is it doing endpoint learning? Like control planning? What's the process? Are you punting packets to CPU? Or?
Okay, so the question is, first, under the bridge domain, we have an option called endpoint data plane learning. And then most of the time, it should always be enabled. But what happens if we disabled? Then first, the only scenario where we can disable is when we use the service graph PBR, policy-based redirection. If we use that feature specifically, then we can disable it. But except for that situation, we can't disable it. And then let's say we are using that feature and then we disabled it. Then what happens is, yes, we don't learn IP information from the data plane anymore, but instead we learn it from the ARP protocol, which was sent to our CPU. So same as the normal router or L3 switches. So we receive the ARP request, punt it to the CPU, and then CPU's control plane will learn it.
And that happens regardless of the ARP flood or GARP configuration?
Yes. All right, so I have 50 seconds left. Does anyone have a really quick question? Yes?
Yeah, just a flex pod that's got VPCs going to leaf one leaf to the endpoints are learning both leaves. What happens with the packet flow when both endpoints are seen in leaf one and leaf two?
So, sorry, could you repeat that again?
So we've got a flex pod environment, you've got VPCs up to the leaves
Mm-hmm.
across, and the endpoints are learning from leaf one and leaf two.
Mm-hmm.
What happens when the traffic comes from another leaf? How does the packet come in? Which leaf does it use to?
I see. So the question is, if we are using the VPC, then the endpoint will show up on both leaf 1 and leaf 2. But let's say if you send the traffic to that endpoint from another leaf, let's say leaf 3, then which leaf 1 or leaf 2, which leaf will do the forwarding? Then the answer is, when we create the VPC domain, we have the one more TEP address that represents VPC domain itself. Then when the another leaf send the traffic to the endpoint behind the VPC, we will send it to that VPC TEP address, which is shared across the two leaves. Then, based on that ECMP routing in the infra network, we will send it either leaf 1 or leaf 2. Then both of them can do the routing or switching. It's not like the standalone VPC where, yes, it does load balance.
Is it per packet or is it per sort of file table?
It's not per packet. It's based on the packet parameter, like a 5 tuples. So if it's the same source IP, destination IP, then it will always be going to the same leaf. Okay? So, all right, that completes my session, and thank you for listening. I hope you guys enjoyed it.